Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the awesome stuff. This is the AAS Journal Author Series. And I am happy to have Ioana Boaca with us today and Maria Gritsevich. Hope I said that right. Maria, Ioana, how are you both doing today? And where are you located, each of you?
We are very fine. I'm located in Ploiești, in Romania.
Okay. Very cool.
I'm in Helsinki, in Finland.
All right, so we got a sort of an international call going here. Helsinki has the snow started yet? Is winter going?
Not yet, not yet. Still possible to swim.
So with a very big suit on, I imagine. So yeah.
Not really.
How about the aurora? Are the auroras happening, or is it still a little too early for that?
Yeah, if you are lucky, you can see it. If you go more north, when you see it for sure.
Well, I like to swim up north too. It's colder. So, Ioana, how about you? How is fall and winter going in Romania?
Yes, the weather is hot compared to the time of the year.
Okay. Wow. Okay.
We have nice weather here.
Beautiful, beautiful. Let's see, it is November 9th of 2022 as we shoot this, and I'm in Phoenix, and we have definitely turned our weather, and so we're definitely into our autumn weather. And it's very pleasant, very nice. So, Ioana, what do you like to do for research?
I study meteoroids, meteors. I will talk about the luminous trajectory of the meteoroid.
Cool. And Maria, what do you like to do for research?
Generally, I do a lot of topics, many aspects of planetary science, and when I do also all sorts of physics like acoustics, light scattering.
Cool.
Very nice. I am a mathematician by training. So.
Very good. That explains all the equations in our forthcoming article. That's where that comes from. Very good. Very good.
So and I would like to start by saying that me and Maria started working on this article exactly a year ago on this date.
Well, happy anniversary. Happy anniversary. And
this is when we first met, like in real.
Yeah.
So Ioana approached me when we met, and I think it was quite successful. Now we are discussing published paper already.
Very cool. Nice. Very good. And that is going to bring us to this very awesome APJ article. It's open access, people, so you can go get a copy for free. Characterization of the fireballs detected by all-sky cameras in Romania. And Ioana, Maria, take us away.
Okay. So I would like to start that by saying that the main purpose of researchers specialized in the study of meteoroids is to recover the remnant matter after the ablation phenomenon under the form of meteorites.
Okay.
This is important because meteoroids have preserved the same composition since the formation of the solar system. And thus, the study of meteorites gives us important information regarding the chemical composition from which the planets were formed.
Good.
Okay. So the most important question we wanted to ask ourselves and to answer in our research is if any of the fireballs recorded with the use of all-sky cameras in Romania could produce meteorites.
Okay.
In order to record the meteoroids entering the atmosphere of Romania, we started developing a network consisting of all-sky cameras with fisheye lens.
Cool.
Called meteoroid orbits reconstruction by optical imaging, namely called MOHAI. We studied this project in 2017, and in 2021, we integrated into the FreePon network in France at the Observatory de Paris. And at the present time, the Mohoy network has installed cameras all over Europe and all over the world. And the full network can be seen in this in the FreePon database. I put the link on the bottom of 9 Fireball. Yes, on that side we can see all the. Okay, yes.
Fireball for Pond. Very cool. Wow, we got a lot of countries here. It's very international.
Yes. We chose to work with decelerated fireballs, meaning the velocity of the meteoroid at the end of the luminous trajectory divided by the velocity of a meteorite at the beginning of the luminous trajectory is less than 0.8.
Okay.
And as we will further see in the following sections, we characterized the fireball events based on the ballistic coefficient alpha and the mass loss parameter beta.
Gotcha.
The ballistic coefficient alpha describes the deceleration rate and is a ratio of masses.
Okay.
And the mass loss parameter beta is a ratio of energies and describes how much mass is lost.
Yes.
Based on those coefficients alpha and beta, we are able to determine whether a meteoroid is likely, if it can, and if it's unlikely to produce a meteorite on the ground because it has fully ablated in the atmosphere.
Right. Okay.
Okay. So, Maria, if you would like to add something.
No, I think I like the way you explained. I think it's very nice. I agree with it. Maybe later I could add more about, or now, like about physical meaning of alpha and beta, but I think you did very well.
Okay, so later when we define alpha and beta. So in section 2, we describe the alpha beta algorithm. The parameters used as input parameters for the study are the meteorite height and velocity.
Yes.
And the algorithm was presented in Gritsevich 2008 and was later applied in Sansom 2019, also in a paper, also in Astrophysical Journal.
Well, great.
Okay, so it is it's an important journal that motivated me to write and to do my research, and I hope that when other people see us, they will also get motivated to send their manuscript to here, because it's a very important journal, and I think it keeps a researcher very motivated.
Okay, okay. You get your next article for free for that one. Okay.
So hopefully maybe people will hear me and they will start reading and writing.
Cover to cover, please. Yes.
Okay.
Very good.
So the
dimensionless. We get our.
Yes. So the starting point of the alpha beta algorithm are equations of 1 to 3 up.
Yep.
Yes, and those are the starting equations that are the equations of motion of the meteoroid, equations 1 to 3. And the physical quantities are m, that is the mass of the meteoroid, V is the velocity of the meteoroid, gamma is the slope, S the cross-sectional area,
Yes.
H is the height above the surface of the Earth.
Okay.
Rho A in equation 1 is the density of atmosphere. Yes, equation 1 and 3. H star in equation 3 is the effective destruction enthalpy. And CH is the dimensionless heat transfer coefficient.
Yes.
And CD in equation 1 is the drag coefficient.
Yes. Okay.
Yes, in order to work with dimensionless quantities, we transform the equations 1 to 3 as follows. We divide the mass, the velocity, and the cross-sectional area to the values at the beginning of the trajectory.
Okay.
And the height to the height of the homogeneous atmosphere, that is 7160 meters. And the density to the density of air near the surface of the Earth, that is 1.29 kilograms per square meter.
Yes.
With those transformations, we obtain equations 9 and 10 that have four unknown variables, M, V, S, and rho. And we have two equations with four unknown variables. And that's why we work under, we add two new hypotheses. The first one is S is M at exponent mu. And the second one is the isothermal atmosphere. These equations assure that equations 9 and 10 have an analytical solution.
Cool.
And the first condition, S is M at exponent nu, gives us the association between the cross-sectional area of the meteoroid and its mass.
Yes.
The parameter mu is related to the rotation of the meteoroid. If nu is 0, then the meteoroid doesn't rotate at all. And the ablation phenomena occurs only on the front side of the object. While if mu is 2 divided by 3, then the meteoroid rotates uniformly.
Okay.
And the meteoroids ablates uniformly from all sides. And we will further see that the extreme values, mu is 0 and mu is 2 divided by 3, are used to classify the outcome of the meteoroid. We classify the domain in 3 regions: if the meteoroid is likely, possible, or unlikely to produce meteorites.
Okay. Okay. Good.
Okay. We go downstairs. Down, please.
I like downstairs.
Okay. Yeah. Yes. There. In order to compute the integral, we need to work with some boundary conditions. Y is infinity, V is 1, M is 1.
Okay.
That's meaning that the initial height is the meteoroid is infinity. It comes from infinity.
Right.
And the meteoroid has an initial velocity and an initial mass. Thus, we
Very cool.
obtain the solution, equations 11 and 12, and we will further see that the fitting how the fitting equation 12 fits our data. I will explain that. I will see that explain you later in a figure. Here, I is the exponential integral function.
Yep.
And alpha and beta are the dimensionless parameters used. Alpha is the ballistic coefficient, and beta is the mass loss parameter. And I like to ask Maria to talk about more about these parameters.
Okay, thank you. So basically, with two parameters, we have very simple physical meaning. This is what I like about them. So when you use them in studying meteor phenomena, you don't do like bare fitting with points are just fitted with a curve.
Okay.
We actually have physical meaning, and you derive them, and when you put them into the equation, and when you see what equation actually fits the data, not what you would just graphically try to smooth the points. So if you look at in the expression for ballistic coefficient alpha here, you would see that ME, and then always other things like density of air in front on the sea level, rho zero, when multiplied by height of the homogeneous atmosphere, and then multiplied by cross-section area of the meteoroid when it comes to the atmosphere, this would be actually equal to the air column in the front of the body, and then be divided to the sinus of the slope. So basically what alpha stands for is the ratio between two masses. First, the mass of the air in this column, which body has to push through to hit the ground, and we divided it to initial mass. So unlike many traditional studies, where we would just watch what's the mass of the body, how big it is, and then characterize it with the mass.
Yes.
I think this is more smart parameter, because this sort of looks at efficient ratio with all combination of parameters. So the smaller mass body could actually be more favorable in reaching the ground.
Yes. Yes. Very good.
Similarly, mass loss parameter beta, so it shows the ratio of kinetic energies. Maybe here it's not straightforward, but if we would multiply it by ME, like initial mass of meteoroid, and then divide by initial mass of meteoroid, then we would have a ratio of initial kinetic energy of a meteoroid when it comes to the atmosphere, divided by the energy which is required to fully destroy this object in the atmosphere.
Yes.
This again would mean that we don't treat all objects of this given kinetic energy equally. We understand that some objects could be made of iron, some objects could be made of ice, some could be made of stone, and this is where beta would come to play, because initial energy could be same, but when to destroy the ice, we need to apply much less energy. So beta would be much higher. So this is something like Tunguska-like impactors.
Okay.
Very high beta. And when if we have something like cyclothealin or other iron falls, when beta is very small, because you need so much energy to destroy the object in the atmosphere, but actually it survives usually regardless.
Very good. Cool. Yep. I'm with you. That was a nice explanation. Very good.
Okay.
And we would later see how with alpha and beta, they could be applied in many ways. They could be also derived in many ways. As Ioana mentioned, this is the algorithm which works well for decelerated fireballs. There are different schemes which could be applied for just ordinary meteors, which are not showing deceleration. But we will come in this paper to very nice applications, how this alpha and beta could be used to actually visualize what's happening with the events with certain outcomes. I think Ioana could continue.
Okay. So in section 3, we presented the results of our research.
Cool.
We studied the events detected by the Freepon network in Romania with the use of Mohoi all-sky cameras over the period January 2021 until April 2022. We had more than 100 detections, and 15 of them, were events with deceleration. In figure 1, I represented the number of weekly detections during the analyzed period, and in the orange are marked the number of detections with deceleration.
Yes, the orange.
Yes.
So what happened in August? Did we go through a meteor shower?
Yes. We had we have a larger number of detections in August due to the Perseid meteor shower, but none of them were with the deceleration.
Right.
Maybe this is because people are in holiday and they look up more and they're not happy.
That's a good reason. There's a bias we should correct for.
Yeah. And
Right.
suddenly more shooting stars spotted.
There we go. There we go. All right. That's figure one. That's our detection.
Maybe we're just eager to make wishes.
There we go. And there we go is some of the
Yes,
distribution.
and in figure 2, we plotted the height extension and declination of the radiants which we studied in this work. All of them are randomly distributed over the sky, and all are sporadic meteors, as I previously said. So as a further application of the alpha beta algorithm, we mentioned the computation of mass. Well, in order to define what is a meteoroid, we have to say two things, and we thought of the shape at the of the meteoroid at the entry in the atmosphere and the material which it's made of, meaning mostly the density of the material. We we computed the mass at the entry at the atmosphere as in Gritsevich 2008 with the formula 16, where AE is the shape factor of the meteoroid, and the final and the final mass of the meteoroid, meaning the mass computed of the end of the ablation phenomena. We compute that with equation 17. And we consider the case when the final velocity is much smaller than the entry velocity, and thus the final mass is computed with the formula 20 at the bottom of the page. Yes, formula 20.
Yes.
Yes.
Good.
And in what follows, we are able to write the mass loss parameter beta as a function of the parameter alpha, as in 21. And we define the boundaries that separate the domain in 3 regions. As I said, the meteorites that are likely, that can, and that are unlikely to produce meteorites. With the boundaries given by the extreme values of the shape parameter mu. Mu is 0, and mu is 2 divided by 3 in equations 22 and 23.
Yes. Expected 3s. Yep. Okay. Cool.
Yes. We took in our analysis 2 cases for the shape parameter. AE is 121. That is the shape parameter of a meteoroid having a spherical shape. And we also consider the density 3,500 kilograms per square meter. That is typical for recovered meteorites. And using this shape factor and this density, we computed the M1 mass. And we took another case of shape factor. AE is 155. That is typical for brick objects that have parallelepiped shape.
Okay.
And we denoted this mass, the M2 mass, that is computed for the shape factor AE is 1.55. So we expect the real shape of a meteoroid to be between those two values or very close to them. That's why we chose those two cases.
Okay.
Maria, if you would like to add something here.
Yeah, basically, maybe it would be easier to do it on a plot already, but I could just add maybe that it's actually still very nice with the passage to with dimensional parameters here, because until this page, what we now covered, there were no assumptions in the study. So when we derive alpha and beta, this is very straightforward. There is just unique couple of alpha and beta for each variable event.
Yes.
And I like it because you don't need any artificial assumptions, any kind of free parameters to be set. They're all inside of alpha and beta, and it's nice. But here, when we want to kind of convert one fusor to mass or to make fusor things, when we have to assume something. So in order to derive mass based on alpha, few things come to play, like Ioana mentioned, density of meteoroid or shape.
Right.
Again, the good thing about it is that if you would think about mass of the meteoroid or cross-section area of meteoroid, which was in the beginning of in our first formulas, these values, they could be anything from 0 to infinity. Now we narrow down to the point that we could actually determine mass or cross-section area or anything just by using this shape coefficient, which is changing in very narrow range, and also density, which is changing in very narrow range, and which could be easily recalculated. So I think it's very cute here. Could be not maybe, or it could be not maybe obvious to a newcomer.
Right. Okay.
But in principle, this is where the trick is.
Very cool. Very good. I'm with you. Good.
I think we should move to the plots, because on the plots we could just explain it maybe.
Yes. On figure 3, we have the distribution of alpha beta parameters in the system of coordinates logarithm of alpha, logarithm of beta. We have the three-point detections in Romania in blue.
Yes.
Blue circles. Yes, the Cavezzo meteorite is marked with an orange square. Cavezzo is the only meteorite recovered by the three-point network. It is recovered by the Prisma component of the three-point network in Italy.
Yes.
And all other meteors from this plot are recovered meteors, yes, famous meteors from the literature. And we can see that all recovered meteors are here in a cluster region.
Yep.
Yes, yes, yes.
One outlier there. Yep. Okay. Good.
Yes.
Yeah.
On table 1, that is down this page, we have the computed entry and final mass for each event. The events are named as by the time they were captured by the three-point network as year, month, day, and time in hour, minute, second in universal time.
Okay.
We can see that we have a wide range of masses. For the M1 mass, the mass ranges from 0.6 to 1083 grams. Yes. And the M2 mass ranges from 1.3 grams to 2,277 grams. So we have a wide range of mass.
Yeah, 3 orders of magnitude.
Yes, and we have one here. We will further see one meteoroid that results in a meteorite production is the one 2021 1024. We will later talk about it.
Okay.
Yes.
Here we go.
Yes, that is the one, but it has a smaller final mass, so it's difficult to find.
Yes, it does. Okay.
So the event name basically stands for the date when it occurred and when time.
Yes. Makes for a nice telephone number.
Well, it would be nice if you could call.
Yeah.
And say, land here, please. And don't go too far.
Yeah, if only one could.
With roof, please.
Very nice. Cool.
So the parameters we take into account when you compute the meteoroid's final mass are the shape factor AE.
Yes.
That is the shape factor computed at the entry in the atmosphere, and the bulk density rho m. We imposed, in order to define what is a meteorite, we impose a final mass of, we consider the cases of 50 grams and 25 grams as a final mass. And we will see in cases 1 to 3 below.
There we go.
Below, yes. In case 1, we determine the outcome for meteorites with the spherical shape, meaning
Yes.
AE is 1.21, and the density is rho is 3,500 kilograms per square meter.
Yes.
We can see here the Cavezzo meteorite that lays in the likely fall region. Cool. So this is validation of our results. And we can see the curves drawn with the use of the shape of the extreme values of the shape parameter mu. The curves are dependent on the slope. That's why we represented them in the system of coordinates logarithm of alpha, sin, gamma, and logarithm of beta. Yes. And those events that are in the unlikely fall region are fully ablated meteors. Okay. It's smoked. Okay. Cool. So the question of the course are given by questions 24 to 27 below for this case. In the second case, we considered brick meteoroids with having parallelepiped shape and the shape factor 1.55. Yes. And those are the values of the course that separate the equations of the course that separate the domain based on in figure 5. Okay. Yes, for the case 2 is in figure 5. Yes. Okay. So this is for meteoroids with brick shape, and shape factor AE is 1.45. Yes. And in the figure 6 below, we provided the outcome of meteoroids with spherical shape, meaning shape factor AE is 1.21, and we considered the values of the density of 2,500 kilograms per square meter and 3,500 kilograms per square meter. Cubic. Yes, cubic, sorry.
Okay.
Cubic. So Cavezzo, in all cases, Cavezzo likes in the likely fall region. So this is a validation of our results, because the
Yeah.
Cavezzo is recovered meteorite.
Nice.
And in case 4, it's an arbitrary case. If we have any other mass or shape different from the ones mentioned above, we compute the entry mass as is mentioned in the formula 34,
Yeah.
where we compute with the two sets of starting for two sets of input parameters, and we
Good.
can compute any other the outcome for any other mass and shape
Yes.
parameter.
Yes, I'm with you.
Yes, and
Cool.
in what follows in the article, yes, we will demonstrate how to apply alpha beta to the event that lies in the likely fall region.
Yes.
So this in this picture, figure 7, we can see the map of Romania and the meteorite
Cool.
detected by two stations, Feleacu and Baia Mare. We
Okay.
can see the luminous trajectory of the meteoroid. So in
They look big.
yes, in figure 8 below.
Aha. Okay.
Yes, we plotted the velocity and the height of this meteoroid. The velocity and height, as I said, are the input parameters for the alpha beta algorithm. As seen by the two stations that detected it. We can see that it's a decelerated fireball.
Yeah.
And in the following figure 9, we plotted the height versus the time of the meteoroid as it was recorded by the two stations.
Yes. Very nice.
Yes.
It's coming down. So it's about a 4-second event.
Yes, it was long. I mean, it's a pretty long event, not extremely long, but it's a long event. Yes.
Yeah. Longer transit. Very cool.
Yes, we had the longest event we recorded was a few days ago, and it was almost 14 seconds.
Oh, wow. Okay.
Yes, that is the longest recorded by the Mohoid. Yes.
Okay.
That and it exits the atmosphere. It's a grazing fireball, the last fireball we recorded.
Cool. Very good.
Yes. And in figure 10 below, we plotted the normalized height versus the normalized velocity of the meteoroid. The blue stars, yes, are the computed points, and this figure demonstrates in practice how to use alpha and beta.
Nice
and
fit.
Yes, the red curve is not drawn using the dots, but the analytical solution of equation 12, which I mentioned in the introduction, and obviously alpha and beta. So we got a really good fit for our
very nice
data.
A priori.
Yes. Maria, if you'd like to add something here.
I think it's a good fit. Yes, I think
Yeah,
it's a good
very
fit.
good. Considering it's
Well,
not fit.
the algorithm is actually designed so that it especially fits the points in the bottom part of the trajectory, which you could still see from this graph. It's quite smart because
Yeah.
in the beginning the scatter is sort of a little bit. It's really hard to get exact values when it goes so fast and so far. So
Right.
hard.
Okay, cool. I like it.
Yes. And
It looks starry, right?
It looks
Lots
what?
of stars. Starry.
Yes, yes, yes.
yes.
Story night. Okay.
Almost like starry
Ooh,
night.
what have we here?
yes, this is a
Major axis.
yes, semi-major axis evolution for it's for the
All right.
meteorite resulting in a meteorite producing
Wow.
yes, it's the semi major semi-major evolution for the a set of clones.
Okay.
And in figure 12, we have the projection of the luminous trajectory of all the luminous trajectories of the 15 events studied in this
With the V greater.
research, and it's in yellow, and the final part of the luminous trajectory is marked with a red dot.
Yes. Okay. Very good. Cool. All right.
Yes. So
Gotcha. Very nice. Good.
thank you.
All right. We'll take it from there and I'll pick up the other part as we go. Ioana and Maria, thank you so much for walking us through your very lovely article. And you kind of touch on it a little bit there at the end, future work. So let me ask, where do we go over, let's say, the next 2 to 5 years? Are there additional, I'm sure there are additional observations in the pipe. Are there alternative theoretical models? Are there other calculations to do? Just sort of where do we go with this topic over the next couple of years? What do you think?
We will continue this applying this algorithm to other detections of the people network and also to other networks.
Okay.
We can improve our algorithm by working with the real atmospheric model instead of exponential one.
Sure.
Maria has worked in one of her articles in with the real atmospheric model.
Mm-hmm.
We can we want also to study events without deceleration, and we want to compute the storm field to the events in the likely for and possible for region, and to go to search for them to make a search campaign.
The ultimate proof. I found it.
Yes, yes.
Very cool.
I think a few more things could be done, like, well, I mean, tons of things could be done, but maybe few to mention is with shape change parameter mu, which Ioana was showing. Okay. So the way, as you now could see, it now sort of, now the main assumption is that, okay, with shape change parameter can't be less than 0. 0 is when it's oriented motion. And yes, this is the conditions for getting a meteorite is most favorable because you get the least mass loss for fixed beta value. And the maximum is 2/3.
Okay.
And we sort of define it as a likely region for meteorites as a kind of, as it was on the paper, this kind of region in between with 2 mu values. But in principle, we were thinking of that we could also incorporate analysis of light curves, because when we analyze light curves, this work was done before in a few papers.
Okay.
Then we could determine not only alpha and beta, because alpha beta use deceleration only in this context at least, or we use basically dynamics, but mu could be determined using the light curve. Which is like from technical point of view, when we would even narrow down with this kind of area. But I don't think it's a big deal, because even now I think it points you directly to which fireballs are likely meteorites, so it's good enough in my opinion. And then also, for example, much more uncertainty comes from terrain, as Ioana was explaining. So sometimes we need to set what is it. Like, we understand that meteorite is something what is recovered or when it is recovered. But when for a computer, we have to define what is a meteorite. So is it 50 grams, 20 grams, or 100 grams?
Right.
So practical uncertainty actually comes from the terrain. If you go for research in Finland, it's very hard to find something like 100 grams. But our colleagues in Australia were good enough when they go to like desert, when they could find something as small as 20 grams. So it's good to keep these things in mind too. So this is from technical perspective. So this mu would narrow down, but I just want to say that practical uncertainties are actually more.
No, good.
But then from the scientific stuff, I think we could also explain, imagine that now that we could work with large data sets, because this would be fully automated and issue of automatic alert. So I think we could, for example, think of using all free-point data from all these countries, what you saw in the beginning, and we could pinpoint something really cool. For example, we could think of finding an interstellar meteor in the database which produces a meteorite. Of course. So there is now interstellar comet, interstellar asteroid, interstellar meteor. So I think this work would be on the way to recover first interstellar meteorite.
Very nice. That would be a find and a half.
Yeah, because this is where you would really need something automated, quick, fast, reliable, physics-based, and something very handy.
That's a prize.
What it is.
That's pretty cool. I didn't thought about that. That's pretty good. Very nice. Very cool. Well, I certainly look forward to this topic evolving over the next couple of years. It'll be very interesting to see if we can get an interstellar one. So it'll be very good. So Ioana and Maria, thank you so much.
Thank you. And
that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Thank you.
Bye-bye. Bye-bye.